Let's start with the first session for today. So our talk title for first session for today is Streamlining Testing in Large Python Codebase by Jimmy. Jimmy, the stage is all yours now.
Hello, this is Jimmy. Today I will talk about how we solve the testing challenge in our large Python codebase. I'm a staff software engineer at Zip from San Francisco. Before I begin, if you want to view the slides on your device, you can scan the QR code. So in this talk, I will cover Python testing best practices, including test coverage, continuous integration, and then talk about the slow test challenges we have in our large code base. I will also present how we use different optimization strategies to tackle those challenges. Finally, I will share some results after those optimizations and recap the takeaways. And at the end, we will have some time for Q&A. We are Zip, a procurement software as a service startup. We try to help our customer business make purchase easier and more cost-effective. Our customers, including businesses in technology, bank, and many other industries. And we have a very large Python code base with 100 developers continuously making changes. And we are hiring rapidly, so the team size is also growing fast. Our code base has more than 2.5 million lines of code, and the size has been doubling every year. The number of tests in our code base and the tech debt are also increasing rapidly over time. Currently, we have more than 20,000 tests. And why we care about tests? Because tests are important for us to ensure our quality on our code changes. We want to make sure our code changes are reliable and correct. We also want to be able to make code refactorings with higher confidence. And tests are also used as documentation of our code, provide as examples. The following are some common test metrics which could be useful to understand your quality of tests. The first is test execution time that measures the time from the test start to test completion. And the test reliability, which can be measure the percentage of how frequently the test pass versus fail. The next is test coverage, measures how many percentage of the code is covered by tests. So in the following slides, I will talk about how you can use different open source tools to implement tests and collecting those metrics in Python. On each of the slides, you will find a link to the open source tool at the top left. So let's say we write in some Python functions and we want to start building tests in it. PyTest is a widely used Python test framework. In order to build a test case for a function like this example, is even, which is a simple function that will check whether the input integer is an even number or not and return true or false. In order to build a test case for it, we can just create a test file named with test underscore prefix. And each test case can be built as a test Python function, also named with test underscore prefix with this, and we can just install PyTest and run PyTest command to find and execute all the test cases. Here we also provide the -vd option. it will display the detail of the test results, so we can see the full qualified name of each test case and whether they passed or not. That can be used to measure the test reliability. We also see the time, which is 0.03 seconds. That is the test execution time. To measure the test coverage, we can use a tool, PyTestCov, which is also a PyTest extension. After install the plugin, we can provide --cov option to PyTest. At the end of the test run, it will show the detail of the coverage, each file, how many statements in it, and how many of them are missed during the test. In this example, we have 80% test coverage on our helper.py. In order to increase the coverage, we can simply just add some more test cases to test the odd numbers to increase the coverage. We usually also implement the continuous integration best practice. The goal is to be able to continuously merge changes with high confidence by implementing automated tests. So the workflow looks like this. Developer, they can submit code changes for code review, and they are pull requests, and we automatically run tests on those pull requests to verify the code change. We only merge a pull request after all the tests pass and after the code is being reviewed and approved. With this best practice, we can ensure the test metrics like the reliability and the coverage are enforced and met the predefined threshold. Now I will show you how to use GitHub workflow to implement a continuous integration. We can easily add a new workflow in .github workflow folder in your project. It's a YAML file. In this example, it's ci.yaml, and we define the name and the events we want to run this workflow. We want to run it on pull request event whenever changes are pushed to the pull request, and also when the changes are merged into the main branch. Then we can define some jobs. So here we define a run PyTest job that use the checkout action to check out the codebase and install the Python 3.13 interpreter, install dependency using pip, and run PyTest. So with that, we have a continuous integration pipeline. Now let's talk about the challenge we faced. Our test execution time increased over time because many factors. The first one, the number of tests continue to increase as developers are building new feature and adding more tests. Also, the codebase size increases. So the test coverage measurement also has more overhead over time. The number of dependencies are also increased. That means to begin the test run, we need to install more dependency. We need to import more dependency. So all those makes the tests much slower over time. We have several strategies to address those challenges. Our first strategy is parallel execution. So a test runner usually has multiple CPU cores. So if we can run multiple process, and each worker process can run different tests in parallel, that can be much faster. In PyTest, we can install the xdist extension, then provide -n number 8, means we want to use 8 worker processes. You can also provide -n auto to automatically use all available CPU cores. So with this approach, we can divide the number of tests by the number of CPU cores. However, we have more than 10,000 tests, so dividing by 8 is not fast enough. So we also want to run tests in parallel on multiple runners. We can use the PyTest split extension to split the tests into groups. In this example, we split tests into 10 groups. And we want to run different group on different runner. So on the first runner, we will provide group number 1. So it will run the first group of tests with this command on the runner. So with this, we can distribute the tests into n number of CPUs and also into m number of runners, which has a lot more parallelism. However, by default, it assumes all the tests has the same test execution. So that means if some test has longer execution time, it will make the overall runtime unbalanced across all runners. To fix this, we can collect the test duration time of each test case. When running PyTest, we can provide the store duration option to collect the execution time of each test case. And then when we split it into groups, we can provide the collected test duration file using the duration path command. In this case, PyTest will try to distribute the test case to different group by considering the test execution time. So we will have a balanced test execution time across runners. In order to implement multiple runner with multiple CPUs parallel execution in a GitHub workflow, we can use the matrix strategy in the workflow config. So here we define a group from number 1 to number 10. And in the job step, when we run the PyTest, we can reference to the matrix.group variable. And by doing this, it will provide different group number index to different runner. If we have 8 cores on 10 runner, we will have 80 concurrent worker to run the tests. Next strategy is cache. So before we start the test, we need to install Python dependency. We usually use pip. It needs to resolve the dependency from the different requirements and then download and install, which can take some time if you have a lot of dependencies. In order to leverage cache, we can use the cache action in your workflow. So here we define a step, dependency cache, and we use the requirements file as the hash key of the cache. That means we only want to rebuild the cache when there's some dependency updates. So if there's no dependency updates, we will just restore the cached dependency without running pip. In the case that we don't need to reinstall everything from scratch, in a large code base, it can be 5 or 10 minutes time saving. To make it even faster, in the case we need to install the dependency, we can use UV instead. UV implements a much more efficient dependency resolution algorithm, and it can be used to replace pip easy. You just add UV in front of the pip command, and that can make the installation much faster. It also downloads the dependencies in parallel, and by default, UV require using vinf. If you don't use vinf, you can just add -- system to install to the system Python environment. Next, we will also look into some non-Python dependencies. You may also run tests with Node.js, so you need to install Python and Node interpreters. You may use some database like PostgreSQL, so you also want to install database or some other system packages like protobuf or Graphics. Or if you are doing integration tests, you may want to install different browsers with different versions, like using Playwright. So those installation could be slow if you have a lot of them. To cache those installation, we can use Docker. In a Docker file, we just define the steps to install those dependencies, like use apt-get install to install Postgres and protobuf. And then we can build a image and publish to a image registry. After that, in your workflow file, you can just specify the image in the container section to use it to run your CI job. With this, you don't need to install everything on every run. In a large code base, it can save 10 minutes or more if you have a lot of dependencies. Our next strategy is to skip unnecessary computations. If we can skip some unnecessary tests or linters, we can run much faster. So we will want to check what codes are changed and then decide what tests to run. For example, we can use the change file action to provide a list of file patterns. Here we define a find PyChanges step to check if any Python file has changes. And then in another job, run PyTest, we can check the has PyChanges. If it's equals to true, that means in this run, there are some Python file changes, and we can only run PyTests in this case. So if we are updating some non-Python files, we can skip the run, make CI run faster. We can also make it more granular. For example, some linters, they may only check files without looking to the imports. For example, black formatting or flaky rules. For those linters, we can just run them on updated file on the pull request instead of always running on the entire code base to be much faster. And also in the monolith, when you already have a lot of tests, if you can try to modularize your code and leverage build system to only run the impacted modules tests, that can also make it faster. So next is about the test coverage overhead. So we mentioned as the code base increase, the test coverage measurement can be slower. It's because by default, PyTest will measure the coverage for all the local files. So it will be slow in a large code base. If we just provide the updated file path as the options to PyTest to the --conf, then it will only enable the measurement on the updated file that can save 1 minute or more on a large code base. Our next strategy is modernize the runners. When you use GitHub runners, the default runner you may feel it's slow when you have a lot of tests to run. In this case, we can look into modernize our runner. For example, if you are using EC2, you can look into different instance type to use the most advanced instance with the optimized CPU and memory combination based on your workload. You can choose the larger CPU or smaller memory size to get most cost-effective performance. If you don't want to bother look into those details, there's also many third-party hosted runners you can choose from, like namespace or buildjet. And to make the runners more effective, we will also want to implement auto-scaling. So in our case, we use EC2 and use the action runner controller to deploy our runners on Kubernetes. And it will automatically, based on the CI round requests, to provision more or less paths to make it more effective. So when we do all those runner optimization, we try to compare with GitHub runners. At the end, we were able to achieve 5x tax cost saving and 2x performance speed up with those optimizations. So let's take a look at some results. So this chart shows the P90 test execution time of our CI. In the beginning, it's more than 30 minutes. And after applying all those big and small optimizations with the strategies we talk about, eventually we can bring it down to like 15 minutes. You can see these charts goes up and down. It's because the developers are continuously adding more tests. So if we do nothing, it will just regress over time. So we have to continuously identify opportunities and optimize our code base to keep the execution time a good developer experience. While we do work on those optimization, we also require some threshold on the test coverage. So on the updated code, on pull request, we require a 75% check. And by applying this check, we were able to increase our test coverage from 50% to 86% in 1 year. So let's recap the strategies we talk about for scaling slow tests. They are parallel execution and cache and skip unnecessary computations and modernize runners. So that's the talk today. If you are interested in our other technology, you can check our engineering blog. If you are interested in job opportunities, you are feel free to check out. So now we have some time for Q&A.
Yeah, so if you have any questions, feel free to ask to Jim. Yeah, you can.
On the optimization that you mentioned, I think you could talk about those. Very interesting.
Mm-hmm.
Which was the best? Like, which was the one that you would go for first in terms of optimization for improving the strategy?
Okay, so the question is, among all those different optimizations, which was the most useful and the most first applied optimization? Yeah, I would say the parallel execution is the first most useful optimization we did by spawning many workers, many runners with concurrent workers. We can easily drop our cost. Yeah, and after that we starting to apply all the different cache to make it even more efficient.
All right, any other questions to Jim? I think seems like there are no questions. Again, Jim, thank you for your time and giving a great presentation at PyCon JP. Really appreciate that. All right, give it a big round of applause to Jim, guys. Thank you.